presenting sepsis prediction with continuous and discrete clinical data leveraging big data tools. Sepsis is a life-threatening condition that arises when the body's response to an infection injures its own organs and tissues, and is one of the leading causes of worldwide hospital stay morbidity and mortality. By identifying patients that will develop sepsis early, medical providers are able to intervene to reduce the patient's risk of death or complication. Not only does this benefit the patient, it also reduces ICU costs relating to admissions. Currently, more than half of patients that develop severe sepsis are admitted to an ICU. Given the critical nature of sepsis, much effort has not only been made to predict its onset, but also to ontologically define its nature. The first well-accepted definition of sepsis in 1991 consisted of 2 or more symptoms of systemic inflammatory response syndrome, but also delineated sepsis from the more severe septic shock. In 2016, the third version of the definition was proposed by Singer et al. What we call the gold standard definition of sepsis moving forward aimed to be simpler and more actionable. It encapsulates infection accompanied by various signs of organ failure. Specifically, suspicion of infection is identified by a blood test and administration of antibiotics within a certain window. Then, from 48 hours prior to infection to 24 hours following it, a SOFA score change of 2 or more is required to constitute sepsis. The SOFA score holistically examines respiration, coagulation, liver, cardiovascular, neural, and renal function. In this project, we use MIMIC3 as our dataset, which contains information from Medivision and CareView management systems. Because CareView reporting consistently underrepresents sepsis prevalence, we only utilize Medivision. As seen, the vast majority of hospital stays thankfully do not amount in sepsis onset. In our findings, it is about 20 to 1. Of 22,000 unique Medivision hospital stays, about 6% were found to involve sepsis. After running through our feature construction pipeline, which drops records missing critical fields, we are left with about 12,000 records and a 3% rate of sepsis prevalence. We detail our end-to-end pipeline as follows. First, we label all hospital visits as sepsis positive or negative in accordance with the Sepsis 3 gold standard described earlier. We adapt the SQL scripts open sourced by Johnson and Pollard for use with PySpark architecture. Label time here constitutes the time of sepsis onset for positive patients and discharge time for non-septic patients. All the hospital stays were first screened for suspicion of infection. Then, within 72 hours prior to infection and 24 hours post-infection, we periodically check the patient's SOFA score. If the hourly change is larger than 2, the hospital stay is labeled as positive. Otherwise, it is negative. We define our index time as 4 hours prior to label time, the point at which we aim to predict septic outcome, which we treat as a binary target. Our observation window starts from 48 hours prior to index time. This serves as our window of inclusion for each patient's derived features, demographic features notwithstanding. Dynamic variables continuously obtained are culled from input and output tables, while discrete event features are generated from lab, microbiology, procedure, and prescriptions. We round out feature engineering with a list of static features from admissions and ICU stays. All features are unioned, transformed, and exported to libsvm sparse format for use with PySpark's ML library of machine learning algorithms. As mentioned, features for a given patient are constructed exclusively from their calculated observation window. We follow best practices for avoiding leakage by reserving 20% of the data as a test set used for final model evaluation purposes only. Due to the severe imbalance between our positive and negative class, about a 20 to 1 ratio, this is a stratified but otherwise random portion of our 12,000 unique observations. The rest of the data is fed through a cross-validation pipeline for model training and hyperparameter tuning. Again, in service to the imbalance in class distribution, we conduct a synthetic minority oversampling technique, SMOTE, to rebalance the ratio to 10 to 1. Using PySpark's built-in ML library, we are able to prototype support vector machine, random forest, and multi-layer perceptron models. Our best performing was the last, a shallow neural network. While our earliest findings suggested 97% accuracy, this was of course misleading due to our label imbalance and served as our baseline. When we switched over to AUC metric instead, we found that our various attempted models had little predictive strength. We settled on a simple multi-layer perceptron model. Unfortunately, we are seeing little generalizability from the model. We attribute this to the severe class imbalance. The test set, while stratified, contains so few positive labels that they might differ tremendously in composition to the positive records used in the train set. Further examination is needed. Regardless, we see that dropping the decision threshold might be preferable for use in hospital settings, increasing the number of true positives predicted at the expense of increasing false alarms. We encountered several challenges in our project. Sepsis labeling, for one, as it included so many dynamic variables from different sources. Given the size of the data, we had to strive for the utmost data cleanliness in the ETL pipeline. The very nature of this problem, positive sepsis labels representing a small portion of hospital labels, lend itself to imbalanced class-specific consideration, perhaps our greatest challenge thus far. Model generalizability suffered greatly as a result. Much more investigation could still be done as well. Pruning features might improve not only model performance, but also generalizability. While we tuned our model for predicting sepsis at 4 hours prior to onset, next iterations of this experiment might entail 8 or 12 hours in advance. Needless to say, the earlier sepsis can be predicted with comparable accuracy, the better. Moreover, the clinical notes provided during a hospital stay provide detailed, free-form information. In a future iteration, we may experiment with various word vector embeddings to represent this rich data.